Welcome to class number 10, session number 2. This session will focus on electronic skin based on nanowires and organic field effect transistors. Organic field effect transistors are a good possibility to prepare electronic skins. When harnessing organic field effect transistors for the development of an electronic skin, one approach is to consider the fundamental chemistry and the engineering requirements as well as the applications envisioned. To address the individual modes of sensing exhibited by natural skin, one can turn to the building blocks of organic electronics, namely the organic field effect transistor. Control over the properties of the organic field effect transistor is accessible by chemical design and engineering of each component of the device. Therefore, the chemical and structural composition of each transistor constituent may be used to impart a separate sensing mode within the device. In developing this mimic of a human skin, the sensory elements of the organic field effect transistor are analogous to the various layers and constituents of the skin. This vision is depicted in the figure presented on the screen. Actually, in this figure, one can see that the dielectric layer is used as a pressure sensor and that the active semiconductor layer is used as a sensor for chemical or biological species. In this fashion, each layer of the organic field effect transistor can be optimized to carry out a specific recognition function. The separation of multimodal sensing among the components of the organic field effect transistor may be considered as a divide and conquer approach, where the electronic skin can take advantage of the optimized chemistry and materials properties of each layer. First steps towards biodegradable electronic skin have been achieved with field effect transistor based on polyvinyl alcohol as gate dielectric, bithiophene derivatives as organic semiconductor, and polyglycolide derivative as degradable substrate. A list of materials that have a high potential in bioelectronics or bio-inspired devices based on organic field effect transistors are presented on the screen. Transistors that are based on these materials are fabricated on degradable substrate, which is often coated with a smoothing layer to reduce the surface roughness of the material. Metal contacts from the gate, source, and drain electrodes, while dielectrics are needed as gate insulator and semiconductors are needed for gate control charge transport between the source and drain electrodes. Examples for biodegradable substrates would include caramelized glucose, edible hard gelatin, and commercially available plastics based on potato and corn starch. Smoothing is effectively and efficiently achieved by rosolic acid, also known as urine, a well-known organic compound with a simple fabrication route. Dielectrics may be chosen among naturally occurring nucleobases, such as adenine and guanine, as well as various sugars such as glucose, lactose, and sucrose, or even caffeine. Glucose, adenine, and guanine are excellent dielectrics with low dielectric losses and high breakdown strengths. Semiconductors employed as indanthrene yellow G, indanthrene brilliant orange RF, and pyrrolene diimide are shown also on the screen. The indanthrene dye are derived from the natural anthraquinone, are slowly biodegradable and found applications as colors in textile, electronics, and food industry. Pyrrolane diamide, a dye which extensively employed in cosmetics and has a remarkably high tolerance, is also demonstrated. Despite these promising features, the current limitation of natural organic semiconductors is their intrinsic low mobility. The dielectric layer of the organic field effect transistor can be exploited to produce a pressure-sensitive response. The primary consideration for a tactile sensitive element design is sensitivity towards a low-pressure events. The approach in the form of microstructuring is used to take advantage of desirable elastomer properties. This approach utilizes soft lithography to create repeating features on the surface of silicon elastomer, polydimethyl siloxane, or briefly PDMS, and therefore forming a highly ordered microstructured film. This approach may be linked to the introduction of highly ordered air gaps that lead to a foam-like material. During compression, the rubber fills the air pockets, leading to further increase in the overall dielectric permittivity of the film. By using the dielectric within the parallel plate structure, it is possible to transduce pressure into electronic signal, or more specifically into capacitance. Figure A on the screen shows scanning electron microscopy images of structured pyramidal and line features and an unstructured cross-section of PDMS film. When the relative capacitance change was compared for both the microstructures and the unstructured thin films of the same thickness, the unstructured film exhibits little response even at higher pressure values higher than 5 kilopascal, while the microstructured films show significant response at low pressure values of lower than 2 kilopascal. Furthermore, the capacitance change also depends on the type of the microstructure used, as illustrated in Figure A. Figure B on the screen shows that compression of the structures changed the initial capacitance as high as 55%, while a film with line patterns shows a smaller change. Nonetheless, the change is still 5-fold larger than the comparable unstructured film. This observation indicates that the using of different types of microstructures can lead to varying pressure sensitivities depending on the required application. This is comparable to the human skin, where in areas such as fingertips have higher sensitivities than areas on a person's forearm. Application of dynamic pressure to the microstructured film demonstrates a tremendous increase in rate of response compared to the unstructured films. Figure C indeed shows the application of pressure step function of 4 seconds. While an unstructured film exhibits a significant delay time of 5 seconds, both types of microstructured film exhibited rapid return of capacitance to the off state of around 100 milliseconds. Therefore, the lack of bulk film deformation results in a greatly improved response while maintaining the elastomer properties. Another possibility that could be of utility for electronic skin application is the use of nanowires. Nanowires are excellent candidates for electronic skin applications, mainly because of their high mobilities as well as because of their miniaturized dimensions that would allow free bending and stretching. A representative example of the electronic skin device with an integrated nanowire active matrix backplane is shown in Figure A. Briefly, germanium silicon core shell nanowire arrays on polyamide substrate are fabricated. Optical images of a fully fabricated electronic skin consisting of 19/18 pixel matrix with an active area of 77 square centimeter are shown in figures B and C. The structure can easily be bent or ruled to a small radius of curvature, demonstrating the superb mechanical flexibility of the substrate and its integrated electronic components. The sensor array employs an active matrix circuitry as shown in Figure D. In this case, each pixel is connected to a nanowire array field effect transistor that actively maintains the pixel state while other pixels are at rest. This presents an important advantage over the passive matrix circuitry where the sensor element itself must maintain its state without the use of an active switching device. Parallel arrays of nanowires are used as the channel material of active matrix field effect transistors and thereby markedly reducing the stochastic device-to-device variation. The high order and directionality of the nanowires that were applied by a contact printing are visible in the same images in figures E and F on the screen. The sensitivity of the nanowire-based pixel to pressure is plotted on the right image on the screen. The plot shows an exceptional pressure dependency for pressure smaller than 2 kilopascal, beyond which the dependence is linear up to the maximum applied pressure of 15 kilopascal. The reduced sensitivity at the high pressures arises from the reduced elastic modulus of the wrapper covering the device. The scalability of the proposed process scheme is demonstrated by the fabrication of the 19/18 pixel array of the electronic skin with a physical size of 77 centimeters square. The letter C with an area of 3 square centimeters is placed on top of the sensor array, followed by application of normal pressure of 15 kilopascal, as can be seen on the left figure. The output conductance for each individual pixel, in this case, was measured and plotted as two-dimensional intensity plot. The pixel signals around the letter C are clearly affected by the pressure applied. The blue pixels are defective. In conclusion, strain or pressure sensors can be fabricated using transistors based on nanowires or organic thin films. In both cases, the technology is still in its early stages. Actually, most of the published academic works on this topic are from the recent years, and still ongoing research are underway. We now reach the end of class number 10, session number 2. Thank you.